Okay, so let's start the next unit by talking about implicit differentiation. Um, Implicit differentiation takes functions that don't really look like the normal functions that we're used to. And instead of having to solve to get y by itself, we can take derivatives where y is embedded within some function. Okay. So when we look at an explicitly defined function, which is like y equals the square root of 25 minus x squared, it is called explicitly because you can very easily tell if this is a function or not. Okay. However, we know that y equals plus or minus the square root of 25 minus x squared is not going to be a function because we have the positive and the negative version of those y values. Okay. So if we went ahead and squared both sides of this, we would end up with y squared equals 25 minus x squared. It's a lot harder to tell from this format whether or not we actually have a function, meaning all the x's only get used once, so like each x has only one y value, or the graph passes the vertical line test, those sorts of things. Okay. So implicit equations generally do not have y isolated on one side of the equation. That's what we're thinking about. So often there's going to be a power on the y term, so like this y has a y squared. That makes it very difficult to solve for y, and sometimes it's impossible to solve these equations for y. Okay. So we are going to differentiate or take the derivative of equations that are implicitly defined, so meaning y is not by itself. Okay. We are going to use a different notation for derivative. In the past, we've used f prime of x, and now we're going to use dy dx. What that little fraction looking thing, and it's not a fraction, but we can kind of treat it like it's a fraction. This thing right here means the derivative with respect to x of the function y. Okay, so we can kind of treat this like a fraction. We can move the y up here next to the d on the top, but it's not like really multiplied. Okay. There were two different men, we've talked about that, who have developed calculus, so we tend to use both of their notations. So one of them started with f prime of x, and one of them started with the d dx, which is kind of annoying that they couldn't just decide which one they wanted at the beginning, but it gives us options. Okay, so let's think about how we would take the derivative of this function exactly how it is. So we've done lots of functions where we've had square roots, so y equals 25 minus x squared, and that square root transforms into a 1/2 power. Okay. So if we take the derivative of both sides, and since we have a y, instead of putting f prime of x, we'll go ahead and use that dy dx. So dy dx is the derivative of y with respect to x. That's going to equal 1/2 times 25 minus x squared to the negative 1/2 power. And then we multiply times the derivative of the inside function, which will be negative 2x. Okay, we can do some canceling, and we end up with dy dx equals, looks like negative x over the square root of 25 minus x squared. Okay, well, if you take a look, this bottom portion right here is y. It's the exact same thing as what we started with. That happens quite a bit whenever we have those square root functions. So dy dx is also equal to negative x over, well, y equaled that square root, so the square root can get replaced with y. Okay. Now let's differentiate the implicit form of the equation. So if we don't have y by its squared, it ends up looking like this. So we've got x squared plus y squared equals 25. When we take the derivative of x squared, we know we just get 2x. And you would think when we take the derivative of y squared, we would get 2y. The difference here is y is a function of x. Okay, right? Y is the same thing as f of x. So just like when we did use, back when we did chain rule, not only do we have to take the derivative of y, we have to do the chain rule. So we multiply times the derivative of the inside function, which is y. Well, the derivative of y is dy dx. So this is the new piece of information from this chapter, really. And then the right-hand side, the derivative of 25, which is a constant with respect to x, is 0. Okay. Let's get dy dx by itself because we're trying to find the derivative, and dy dx is the derivative. So we'll subtract 2x from both sides. And we get 2y dy dx equals negative 2x. Divide both sides by 2y. So we get dy dx equals negative. Those 2's can cancel out, so we have x over y, which is exactly what we got when we did the problem over here.